Hi and welcome back. So I decided to not do a simple pulley part 2. Kind of figured that simple pulley part 1 was kind of more just an introduction to pulleys and really shouldn't be talking too much more about it. Let's just dive into some problems. I think that would just be much easier. Just makes more sense to me. So in the end, we're going to have 3 pulleys instead of that one. So we got this one right here. That one's going to be stationary. And we got this one right here. That one's going to be moving with A. So it's going to be having the same velocity and acceleration as A. And we have this one C. That's just kind of going to be moving everywhere. So that's why I kind of labeled it as C. So so just to start off, we gotta create a datum. So that's our first thing. So a datum means that it's just a stationary spot that we're measuring from. So we can't do this pulley because it's moving up and down, so it's not a datum in the end. So a datum is just a stationary spot. And we're going to be measuring a bunch of distances from there. So we're going to start off with dA. So our first distance is going to be this distance right here. So we're measuring from the datum to A essentially, but we're going to stop. We're going to stop right here. So reason being, this pulley is moving with A. So we're just going to go right there just so that we can make more sense of the ropes and the rope lengths in the end. So yeah, A's acceleration and velocity is literally going to be the same as the pulley right there too. So we have dA, and then we're also going to have another distance right here. So we got DC. So DC, our distance to our pulley C in the end. And then we're going to have dB as well. So dB. So yeah, and you can have multiple datums. They don't have to necessarily just be vertical ones like that. You can have like even a datum like right here as well. But it has to be a stationary spot like I was saying before. So yeah, so let's begin. So basically we have with this pulley problem a mass for both the blocks right there, both the weights. So MA is 3 kilograms and MB is 1 kilogram. So our final objective in this is to figure out which way it's going. Like, is A going to be shooting down or up, or is B shooting down or up, So let's just figure that out, the acceleration and everything. So the only way we can figure that out is some of the forces, obviously, and all that good stuff that we've learned before. So we're just going to keep adding on to that. However, we're adding on to the fact that we have all these ropes and everything, and try and make sense of this confusion right here. So first thing first is we gotta organize this confusion. So we have basically we'll just say L1. L1 is going to be the length of our first rope. So this is going to be our first rope in the end. So yeah, so we're going to also have some lengths that will change, but we also have some lengths that will stay constant. So I'm going to put RC, so rope constant, because we're going to have a lot of different spots where the rope is just not moving in terms of length. So it might be moving, but the rope has to occupy that much area. So like for instance, this is part of RC. So that length is going to be constant. And we're also going to have this length right here. That's going to be constant. So it has to go around the pulley right there, regardless of no matter how long dA is, or DC or dB are. It really doesn't matter in the end. We're also going to have this length right here. That's going to be constant as well. So going around that pulley in the end. I think that's for the most part all the constant ones. So we have this distance, that's dA obviously. We have this distance as well, that's not so much obvious, in this distance as well. So So moving forward, we're just kind of like going to say RC is just the constants. So I'd love to say RC1, RC2, RC3, but literally it's just going to make things more confusing, adding on more of those. We're going to say it's a rope constant, you know, so it's just a certain amount of length for the rope. That's just constant. So yeah, let me get rid of those real quick. So those are there, but we also have to deal with this length as well. So yeah. So we did this length. Now we got this length, dA. So that was the simple one earlier. And then we have this length that's accounted for RC. And then we're going to have this length right here. So this length is going to be computed with DC, or dA, so this total length, minus this length in the end. So dA minus DC. And we're also going to add in this length as well, because we have another rope constant right there that we're going to jumble into there, you know. Yeah, so anyway, so this length in the end, really, we should make that deep. So makes more sense to measure it from here because we're measuring the rope in the end, you know. Like we did with the pulley right here, B is going to be accelerating and it's going to have the same velocity right there as well with the attachment. So anyway, so we have dB minus DC. Okay, so that's this length right here then. So so yeah, so let's simplify that real quick. We get L1 equals RC plus, so we have 2dA, so 2dA, and then we are going to have 1 dB, and then we're going to have minus 2 DC. Okay, that's D. Oh well. So yes, so this is going to turn into, basically this is going to be our length formula, so we just got to subtract things, and we're also going to take the derivative as well. So if we do, I guess, another version of it, so like let's say this is just a random length, but let's just say the initial condition, so initial. So our initial condition, so L1 is going to be constant. It's going to be the same length. RC is going to be constant. We're literally just going to rewrite this as dA naught, and then dB naught as well, minus 2 dC naught. Yes, this is a C. So basically, if we subtract these equations in the end, we'll get our distance formula. So we gotta subtract the whole thing in the end. So we're gonna get a 0 right here. RC plus R minus RC is 0 as well. So that makes sense. That's kind of why I just kind of jumbled them all together. They're gonna subtract out anyways, so they're constant. And then we're gonna have basically 2dA minus 2dA, so it's going to be 2, and then I'm just going to say delta dA. So final minus initial gives you your delta, your change. It's just going to be dA minus dA naught. And then we're going to get the same thing right here. So we're going to get delta B then in the end. And then we're going to get minus 2 delta C. So So that's one of our first equations. So I'll just write it over here. Start off. So 0 equals 2 delta A plus delta B minus 2 delta C. Okay, now that I got that erased, we're going to move forward. So let's just do the next rope. So let's just get that done, knocked out of the way, and then we'll continue on. So yeah, because it's easier if we just combine them first. So we're going to have L2 now. So I'm just going to leave an RC in there, like normal. So L2 is going to be this rope right here. So it's a constant length. So this is going to be RC. We're going to have a DA involved. So DA. And then we're going to have this, which is DC. So plus DC. Okay. So if we do the whole initial thing again. So we have L2, that's the same. RC plus DA naught plus DC naught. That's a C, not a E. Anyways, so if we subtract our equations, we'll simplify it and we'll get another delta equation, and then we'll combine those two. So we get 0 equals 0 plus delta A plus delta C. Okay, so therefore delta A equals negative delta C in the end. So we're going to combine that with our other one then. So we're going to put that up here. So negative 2 delta C, that's supposed to be a C. That's going to be really just 2 delta A. So let's just rewrite that real quick. 2 delta A plus 2 delta A is going to be 4 delta A in the end. So we're just going to erase that. We're going to change this to a 4 in the end. So yes, we got 4 delta A plus delta B in the end. So really that just translates to 4 delta A equals negative delta B. Anyways, so now let's just take our derivatives of our equations. So if we take the derivative of our first one, we're going to end up with, so the change in length of our total rope is just constant, so that's 0. This is constant as well, so 0, 0, 0 equals 0 plus 2VA plus VB minus 2VC. So yeah, so that's our first equation. So it's really similar to this in the end. We're just going to get like the same equation, so it's just going to be derivatives versions of it. So just kind of showing you how to get them. So let's take the derivative of this now. 0 equals 0. You know, rope is constant. The constants of the rope, that's 0 as well. So, and then plus VA plus VC. So let's implement this then, because this is literally just VA equals negative VC. Just like we saw earlier with the delta equation. Implement that into here, and then we're going to get 4 VA, and then just because this is going to turn into 2VA. 2VA plus 2VA is literally going to be 4VA in the end. So we got 4VA left right there. This is just 0. So and then I'm going to subtract VB over here, so negative VB. So yes, so one of our equations now is going to be VB equals negative 4VA. So the tricky part about this, though, so I probably shouldn't have written it right there, but before you do that, you need to, probably convert your coordinate system. So normally we're working off of that when we're doing free body diagrams. So we're just gonna want to stick with that in the end. Literally, this distance is measured like this right here. Same thing for this one. So, and that's pointed down, so that's pointed in the negative direction. So we're going to have to multiply a negative for VB and VA whenever we see it. So this is going to turn into, so that right there, let's turn into 4 negative VA. So this is very important, just because you're not always going to have datums that are going to end up like, making it easy like this. So sometimes when you convert to the coordinate systems like these, then it could be off. So anyway, so negative VA, so it's putting in the opposite direction, and then we have, same thing happening right here, so negative VB. So when we multiply a negative on both sides of the equation, it literally just makes it the same. So it's kind of a stupid one right here, just because the equation just does not change. However, you do need to take into account that this is our new coordinate system that we're working with. We're not dealing with these distances right here anymore, but this is where we start from. So yeah, when you convert to the coordinate system, you're literally just going to get this thing again. Yeah, just make sure you put in a negative VB if necessary, or a negative or positive VB. So if the datum was down here, it would be positive, So this distance would be positive, and it would be going in that direction. So that is not the case, but could be the case as well. So you just got to be very careful about that. So we have to change our coordinate system first. So having done that, now we can implement it. We can take the derivative of this now. So we take the derivative of that. So we get AB equals negative 4 AA. So the acceleration of A. Okay, so now this is great. This is wonderful. We have our delta equation, we have our velocity equation, and we have our acceleration equation. So let's just analyze that real quick. So let's just analyze the velocity equation. So if our velocity is going up here, it makes sense that this block's going to be going down. So it's going to be creating less slack in the end for this larger rope, and then causing it to go down, and I guess less slack right here too. So less slack means more slack in the other spots. So if VB goes up, kind of makes sense that VA is going to go down. If VA goes up, then VB is going to go down, vice versa. So that's kind of how that goes. And then so now let's start analyzing with free body diagrams like we should. So I'm going to first start off with this pulley. That's going to be the easiest. So if we do the sum of the forces at C, that's going to equal 0 in the end. So keep in mind, whenever we're doing these pulley problems, the pulley is 0, the mass of the pulley is 0, and the mass of the rope is 0. So those are always negligible. These are going to be much thicker objects in the end, and I understand that I did have some ginormous pulleys drawn, but that's more for drawing purposes, so you can see it a little bit better. Even then, if these were to size, this could just be denser material for A and B, so obviously. So therefore making it negligible. So yes, if the pulley is massless, that's going to be equal to 0 right here. So this free body diagram. And then we're going to have basically so we're going to call this just F. So the force in this longer rope is just F. So the tension in the longer rope is F. And the tension in this rope now, that's just going to be T. Sorry. So we're going to have T minus 2F. So what do we know? Well, T is going to equal 2F then. Awesome. It was much easier to start with our pulley. So reason being, because it's massless. So, faster way of going about it. So then picking the mass ones to start off with. So pick the massless. It turns into a static equation immediately. And then you're able to simplify the tensions. Oh, the tension in this smaller rope is going to equal the 2 times the tension in the longer rope. That's what that is. So now let's do the sum of the forces. It's an awful one. They're always pretty awful, but whatever. You understand. So FA. That's going to turn into, we got mass times by acceleration. So mass of A times by the acceleration of A. Then that's going to equal, so like right here, we're going to have an F pointing up, an F pointing up, it's a longer rope, but then we're going to have a T pointing up as well. So we have a T, we have an F, we have another F. So that's going to be, I'm just going to implement what T is immediately. So we're going to have basically a 2F for this tension, and then we're going to have these 2 F's as well. So I'm going to say 2F. So really that's going to be 4F in the end for A. And then we're also going to have to take into account its weight. So it's pulling down with mg, So it's going to be ma times by g. So if we rewrite that, then we get 4F is going to equal, oh, we got to make that negative because it's pointing down. This is going to be negative. Okay, cool. We rewrote that as negative. So if it's negative, we're going to add it over here. And then I'm going to take out MA from it all. So AA plus G. Yeah. So that's our first equation. And then we're going to deal with this one. So the sum of the forces at B, that's going to equal mass times acceleration, of course. MB by AB. And that's going to equal, so we got a F pointing up right there. And then we have a weight pulling down as well again. So we got F minus MB times by G. Add that over there, and then we're going to get F equals MB parentheses, and we're going to pull out MB from it all. So AB plus G. Yeah. So and we're pulled out MB. So cool thing, we know what F equals. It equals that. So we're going to just implement that into there. So we're going to have 4. So 4MB AB. So we're going to just do it in terms of AB because it's a little bit easier, or AA actually. So does make more sense to do it that way. So minus 4AA plus G, so substituted that in. And then we're going to have this side of the equation then. So it's going to be MA, parentheses, AA plus G. So literally all we did was we just shoved this into right here. So that's just that, and then we also shoved that into AB. So yeah, so that's all that went down right there. So now we have only one unknown, and that's beautiful. That's what we need. That's what we want, you know. So if we have 2 unknowns, we need 2 equations, so and so forth, and yeah, so we have enough equations in the end, and we've simplified it to 1 unknown, 1 equation. So let's solve then. Let's solve for AA. So in order for us to do that, we got to get all the AA's on one side and all the other junk on the other side. So everything that's not an AA in the end. We're going to have to distribute that. So distributing that, we get 16, so negative 16 MB AA plus 4 MB G equals MA AA plus MA times by G. So we're going to get that. Or actually, since this is negative, we're going to bring this to this side. And then we're going to bring that guy to that side, obviously. So then that's going to turn out to be basically, when we add this over to here, or subtract the G over to this side, we're going to get basically there's going to be a G in that one and a G in that one. So we can pull out a G. So we're going to have G and then 4MB. And then since we subtracted this over here, it's going to be minus, and then MA, and then times by G. So we took it out now. So that's going to be the left side. So this is the junk, everything that's left over from AA. So now we got AA now going to be on that side. So, and we're going to kind of do the same thing that we're doing with G right there. We're going to pull out AA just to kind of speed up things. So naturally, that's just going to be MA then. And then we're going to have to add, so because we're adding that to this side, and then 16MB. So now let's divide both sides by that. So then that's going to turn out to be AA equals G 4MB minus MA, all that over this guy then in the end. MA plus 16MB. So yeah, let's go over that before I erase it and move on then, just to, further clarify things. So we first started off with our length equations, and we got our relations right here, So anyways, so we did our free body diagram. So we did a free body diagram of C. We got our relation between the tensions, the different tensions. So T equals 2F. We did our free body diagram of A, and then got this equation, then our free body diagram of B, got this equation, plugged this into here, And then we're also able to plug in this guy into there as well. So we have just AA, and then we just solved for AA. Simple as that. So just did a algebra from here on out. So yeah, not too bad in the end. Okay, now moving on. Now that we got it all cleared up and we got our equation for AA right here, we're going to move forward by getting the acceleration for B, the equation for that now. So we're just going to simply use this equation, and then we're going to plug in what A is, the acceleration for A, right here, So we're going to plug this in to this equation, and so basically it's just this times by -4. So when you multiply by -4, of course 4 is going to stay on the outside, but we're going to implement the negative sign within here. So once we do that, this is going to be negative, and this is going to be positive. So literally just going to flip-flop back and forth, switch around, pretty much, not back and forth, but switch around, and then, yeah, we're going to have that 4 out in front. So anyways, so it's going to be 4G, and then MA minus 4MB. And that's going to turn out to be, over 16MB plus MA, because the denominator did not get messed with at all. So, anyway, so we could just go forward with this equation and, call it quits. Just pretty much implement these and be done. But let's not do that. Let's analyze to see if these are even correct. Get some good practice in. This is just for practice right now anyway. It's not a grade. You're here for, better yourself. So let's really go for it, So this is the fun part of all this, like seeing how, things can relate back and everything, and I guess not even back. So like, for instance, for this scenario, what we're going to do is we're going to say that one of these masses is non-existent. We're going to say there's no mass at B. And then we're going to analyze the acceleration of A. And we're going to do the exact opposite. We're going to say the mass of A is 0, and then we're going to analyze the acceleration of B. So when we do that, so for this first one, MB is going to be 0, because we're analyzing the other acceleration. So at MB equals 0, this is going to be 0, equals 0, and then this is going to be 0 as well. So it's going to be over that. So anyways, that translates to G times by negative MA over MA. Masses cancel, and we literally get negative G, which is so cool in my opinion. So cool. Like, it's so cool. Like, how is that not cool? So everything is massless. The pulleys and the ropes. And if we say this is now massless, that MB just doesn't have any mass, well, what's going to happen to the acceleration of A? Well, it's just going to have a negative it's just going to have free fall. It's going to fall down at negative G. So, which is perfect. That's what you want in the end, So it's cool how this works out in the end that way. So we're going to see if we can get negative G down here then. So we're going to try with the acceleration B. We're going to have the mass of A equals 0. So at MA equal to 0, what do we get? So MA equals 0, so that's 0. This is 0. So it's just going to be this over this, and then that times on the outside as well. Anyway, so it's 4G negative 4MB over 16 MB. What will we know? The mass for B cancels. And then also 4 times 4 is going to be 16, so that will cancel with the denominator. And then what are we left with? Negative g again, you know? Like, holy shit, isn't that cool? Like, I think it's cool, but I don't know. You don't have to think it's cool. But anyways, we're just here to learn, and like I think that's super cool that we can like analyze it and just say it's just free falling now. Super cool in my opinion. So it's cool seeing how things tie back together in the end. And anyways, so let's finish off this problem because I'm sure you're antsy to finish this. It's a long one. So now we're going to implement our masses simply. So acceleration of A is going to be 9.81, and then 4 times by 1 is going to be 4 minus 3. It's the mass of A over 16 times by M. Oh, we got to implement them. So 16 times by 1. It's going to be 16, so we're just going to forget that part. 16 times by nothing. Well, shouldn't say nothing, that's a 0, but you get what I'm saying. Times by 1. Times by 1. And then mass of A is going to be 3. So go to our trusty calculator. Let's turn it on. It's so weird. Like, I feel weird turning on an emulator. Like, must start the program. So should just be on naturally, but whatever. So we have 9.81. And then literally this is just going to be 1. So divided by, and then that's going to be 19. So the acceleration of A is going to be 0.5. What was it? 163. 163. That's going to be meters per second squared. So G is in meters per second. So, and then this is going to be kilograms of kilograms. So, well, meters per second squared. So acceleration is going to give you acceleration in the end because the masses will cancel out. So unit-wise. Anyways, so let's do a B. Let's do the acceleration of B now. So it's going to be 4 times by 9.81. And then MA, that is 3 once again, minus 4. 3 minus 4. Really, that's negative 1, just like this was a 1. And then, so that's the numerator. Let's go to the denominator. It's going to be 16 times by MB, which is 1 again, plus, and then MA is 3, just like with the last denominator. Anyways, so we're going to literally get pretty much 4 times by our answer. It's literally what it is. So, it's going to be negative, so let's do negative 4. Boom. So we got negative 2.0653. That's meters per second squared. Again, kilograms cancels out, and you're just left with the units for G, which is meters per second squared. So now, if we analyze it, we're saying B is going to be moving down. at 2 meters per second, and then A is going to be moving up at half a meter a second, which is really cool to know because technically B is lighter than A, but B is going to be moving down and A is going to be moving up. And then this has no outside interaction. So it's almost like this weighs less. But that's not really the case. It doesn't. A has it's got more mass, however, it's got more forces happening to it. So it's got F pulling it up, T pulling up, another F pulling it up. T is just 2F, so it's going to be 4 forces compared to the 1 force right here, this F. So, yeah, I mean, real cool stuff. Real cool stuff, in my opinion. So, hopefully it's real cool stuff in your opinion. If not, just get through the class. So, this is Pulley problem 1. So we're going to have 2 and 3 next. Hopefully those blow your minds just as much. Probably not, because it's not this cool thing at the end where we have negative G. I love how that kind of like came back to like, yeah, it's just free fall. Real cool example in the end. So real cool example. Anyways, I am out. See you in the next video.